Let's do that actually. Still do.
Okay, so we can begin if you are ready.
Great. Let's do that. Okay. Okay. Can everybody see that? How is that? How is that?
Um, yeah, yes, it's good. So welcome everybody to the last talk of the day, and we have Brooks Thomas from Lafayette College, USA, and he's going to talk about cosmological status and its observational signatures. So maybe I can send you a reminder when 5 minutes are left.
Sounds good. Oops, sorry about that. Okay, great. All right, folks. So, good morning. I know it's not morning for most of you, but it's morning for me here on the East Coast of the United States. And I'm Brooks, and I'm going to talk a little bit today about cosmological stasis, which is uh, a novel cosmological phenomenon, which my research collaborators listed here at the bottom of the slide, and I have uncovered within the last couple of years and have been exploring because we think it might be an important piece of the cosmologies to which certain kinds of extensions of the standard model lead. And so today, what I'm going to do is I'm going to talk a little bit about what stasis is for those of you who might not be familiar with it or haven't seen a stasis talk before. I'll talk about the different kinds of realizations of stasis. Stasis is a fairly robust phenomenon, then there are many different realizations of it. And finally, I'll talk to you a little bit about some of the potential observational signatures and phenomenological consequences of cosmological stasis. So, in other words, how we might learn if this phenomenon occurred during the early history of our universe. And again, this is work done with a lot of these folks here, Daniel Hoover and Anna Paulson on this lower paper here were undergrad students at Lafayette when they began their involvement in this project. Anna's now a grad student at Brown. Okay. For some reason, that is not advancing. Hold on. All right, there we go. All right. So, our the general starting point for this discussion is the following. So there are a wide variety of different scenarios for new physics that predict towers of massive unstable states, states with a broad spectrum of masses, cosmological abundances, and lifetimes. And such towers, they arise generically in string theory. They arise generically in other theories that involve extra space-time dimensions. So, of course, you should be thinking KK towers here. They arise in scenarios with confining dark or hidden sector gauge groups. And they arise in scenarios which lead to the production of primordial black holes with an extended mass spectrum. So the black holes themselves are the tower of states. Even though their masses are sort of a continuum, they still constitute a tower of states. So in many cases, these states can give rise to astrophysical signals, signals at colliders, depending on the mass scales and the lifetime scales involved. In other cases, the states are too heavy or too short-lived to be able to be detectable in standard ways. But of course, that does not mean that they have no consequences physically that we can probe, because they can have an effect on the early universe. And in particular, I'm going to be talking about the part of our cosmological history before Big Bang nucleus synthesis and neutrino decoupling. So between the end of inflation and BBN. There are a lot of different possibilities for what might have happened. Of course, there are ways of probing them, and we'll get to that later on. But one of the possibilities that I'm going to try to convince you of today is that such towers can give rise to epochs of what we call cosmic stasis or cosmological stasis. These are epochs wherein the abundances of multiple cosmological energy components, so things like matter, radiation, vacuum energy, kination, things with well-defined equations of state, these things remain effectively constant over an extended period. So what I mean is, as the universe expands and the energy density drops, so the universe is still expanding here, as the energy density drops, the energy densities of the individual components are dropping in a fixed proportions to each other. In other words, the cosmological abundances are constant. So yes, the energy density is still decreasing, but everything is sort of doing decreasing lockstep. And I'll try to explain how this can arise in these kinds of theories. The reason that this phenomenon is, we think, something that behooves a bit more study is that these epochs are often global attractors within the cosmological scenarios in which they arise. So if the basic conditions under which they arise are satisfied, the universe is going to evolve towards stasis. Again, I'll show this later on. So these are likely to be pieces of the cosmological timeline or cosmological history of these kinds of BSM theories that give rise to these towers. And therefore, this kind of behooves us to kind of investigate their impact on early universe cosmology in a little bit more detail. Okay, so how can stasis arise? So in order to see this, let's just consider a simple case where the universe consists only of massive matter. So equation of state parameter W equals 0, and radiation, equation of state parameter W equals a third. Okay, so if all we have is cosmological expansion, the Boltzmann equations look really simple. They look like this. The energy density of matter falls like a volume factor. The energy density of radiation falls faster because of redshifting. And basically, if we rewrite these equations in terms of abundances, the matter abundance goes up to 1, the radiation abundance goes down to negligible, and the story in the long term is that you get a matter-dominated universe. Okay. End of story. However, we are talking here about particle physics motivated cosmologies. And when we're talking about particle physics motivated theories, there can be extra terms in these Boltzmann equations. And so these extra terms, one can imagine, for example, a pair of source and sink terms which function sort of as a pump to pump energy density from matter, which has the lower equation of state parameter, to radiation, which has the higher equation of state parameter. And one possibility, just staring at what these equations look like, is that if the pump has the right time dependence, it could actually cancel off the expansion term in both of these equations and leave basically leave the matter and radiation abundances constant, basically make the right side of each equation 0. How would I do that? What do I need? Well, if it's pretty easy to see, if the abundances are constant, then the only piece of this expansion term that has time dependence is the Hubble parameter. In a universe like this with matter and radiation, the Hubble parameter is going to go like 1 over T. So the pump term here better kind of go like 1 over T as well to counteract the effect of expansion. Okay, so how can such a pump arise in practice? Well, one natural mechanism through which energy density can be transferred from matter to radiation is particle decay, right? If I have some heavy particles where most of the energy of that cosmological component is mass energy, and these particles are decaying into much lighter particles, which act as radiation. That transfer of mass energy to kinetic energy basically functions as such a pump. But of course, if I have one decaying particle species, that energy transfer is going to occur over a relatively short time period, or in other words, most of that energy is going to be transferred at time scales roughly around the lifetime of the particle, and that is not a pump that goes like 1 over T. However, if we have a tower of matter states, let's call these states phi sub L, where L labels the states in order of increasing mass. So if we have a tower of states, and the decay widths and abundances of these states, the initial abundances at some time t naught, where we start the clock, scale across the tower as a function of their mass in some particular way. If the scaling relations have the right properties, these can indeed give rise to a pump that compensates for the effect of cosmic expansion for an extended period, one that does go like 1 over T. And this, as we'll see, is why we expect stasis to be a fairly common feature in BSM cosmologies. We've already discussed that towers of massive unstable states like this are a fairly generic feature in well-motivated extensions of the standard model of the sort that we've talked about. Okay, so to motivate why scaling relations that actually give rise to this behavior for the pump are not a crazy idea, first of all, let's think a little bit about what you actually expect the scaling relations to look like from these theories. Well, very often in KK theories, for example, if I have a flat extra dimension, the mass tends to scale like m naught plus delta m, where delta m basically goes like the inverse radius of the extra dimension, times L, the label that labels the mode, times some index delta. If I'm talking about a flat extra dimension, that delta is 1. But if there's brain bulk interactions and things like that, this delta can take other values. In other theories beyond the standard model, you also often end up getting something that looks very similar to this as far as the mass scaling. In other words, you're sort of getting a power law of the mode number. As far as decay widths and initial abundances, you often are also getting power law behavior. Power law as a function of the mass of the state. So the decay widths, we will just parameterize this as mass to the power of some index gamma. That's our power law index for decay widths. And for abundances, initial abundances, power law of the mass with power law index alpha. So we've got 3 power law indices, delta, gamma, and alpha. Now, again, I've presented this as sort of an ansatz, but these are the kind of scaling relations that you get out of these kinds of BSM theories that involve towers. If I have KK excitations of a 5-dimensional scalar, as I've said before, delta goes like 1 or 2, depending on the relationships between the fundamental scales, like a brain mass scale and the radius of the extra dimension, which is setting your KK mass scale. Bound states of a strongly coupled gauge theory give rise to Hagedorn-like behavior, so this gives a delta of 1/2. As far as decay widths go, if you're decaying through a contact operator of dimension D, this is a natural way of getting a power law scaling like this. Gamma in this case ends up being 2D minus 7, basically. And as far as the abundances are concerned, well, that really depends on what mechanism is producing these states. But the point is that regardless of what mechanism you're talking about, misalignment production of the states through the evaporation of primordial black holes, gravitational production after inflation, decay from the inflaton itself, thermal freeze out, all of these things, basically you end up with something that looks roughly like a power law over an extended sort of range of L. And that's the point. So basically, these kinds of scaling relations are things that occur very commonly in these kind of BSM theories. And as I'll show, they can give rise to a cosmological stasis. So I'm showing here just a simple example. One can do, the mathematical derivation as well, but I think it's a little easier to just sort of see it in things in action. So in this example, the parameter choices that I'm showing you here, I'm just choosing some values of alpha, gamma, and delta here. And I'm taking an ensemble of 300 states. So the individual abundances of these states appear on the bottom. These are these yellow, orange, and blue curves that are color-coded according to this color bar on the right side. And the overall matter abundance in this two-component universe is given by this orange curve here. So we're going to start the system far away from stasis by having all of the energy density initially in the matter states. So initially the matter abundance is 1, and then as these states decay, the matter abundance drops, and now you have an admixture of matter and radiation. So at that point, the matter states, the individual matter states, which act like matter, their individual abundances begin rising. But of course, they only begin rising up until timescales roughly around where the decay lifetime of the individual mode is. Once they get to there, it falls again. And however, since there are a lot of states, once that falls, there is another state to pick that up. And then when that state falls, there's another state to pick that up. You add together the contributions from all of these different states, and the matter abundance, what it does is initially begins falling, as we've seen, but then it begins to plateau and then reaches a regime where it remains flat for a very long period. This is the stasis epoch here. Now, one of the nice things about stasis is that there is a natural, graceful exit, quote unquote, from stasis. Once you have no more matter states left, once the longest lived of these states finally decays, you've basically dumped all your energy density into radiation, and the universe just becomes radiation dominated again and segues very nicely into the standard cosmology. Of course, when you have a very small number of states left in your tower, you can have these sort of edge effects that you get at the very end of stasis. But the point is, there is a very long number of E-folds of expansion here. So again, I just want to be clear, by E-folds, I'm not suggesting that this is inflationary. It's not. I'm just, using a logarithmic scale for the scale factor. So the number of E-folds of expansion here is this N at the bottom of the plot on the x-axis. You can get a very long period of stasis, and this is just one example. You can actually get things that are far longer. The other important thing here that I want to emphasize about this illustration is what the stasis abundances are. You'll notice that in this two-component universe, the abundances of matter and radiation here are the same. They are both 1/2 during stasis. However, I want to emphasize that this is not always the case, and in fact, it's not even usually the case. The stasis abundances are determined by what the values of alpha, gamma, and delta are. So as long as alpha, gamma, and delta satisfy some, basic conditions, one of which, of course, is that these abundances have to be between 0 and 1, obviously. Otherwise, you won't end up otherwise, if that's not satisfied, you won't end up getting a stasis. But for a broad spectrum of possible combinations of these parameters, you do end up getting a stasis. And so if I change the values of alpha, gamma, and delta, I don't wreck the stasis. What I do is I change the balance of matter and radiation during the stasis. Now, what's interesting about this, why do we care? The reason that we care is that the effective equation of state parameter for the universe during stasis, well, if you think about it, this is constant, right? Because these abundances are constant. And what it is, W bar, this effective equation of state parameter, it's a weighted average of the individual equation of state parameters for matter and radiation. And the weighting is by abundance. So what's going on is that we're basically getting a universe that has a constant equation of state parameter that's basically kind of acting as if it were filled with a perfect fluid with some equation of state, but where that equation of state parameter takes a non-canonical value. It's not 0 or a third or 1 or -1 or -1/3 or something like that you typically get out of particle physics motivated cosmologies. Here in this example, it's a 1/6. That's weird. And so you end up with getting cosmological epochs that are a little bit unusual and in which the universe is behaving in kind of a non-standard way. And indeed, so that's one of the consequences of stasis that we're going to explore. Now, the other reason why we care about this is that in these theories, if you have the scaling relations, alpha, gamma, and delta, that are in the right ballpark, in the right that have the right properties to give rise to stasis, you are basically going to evolve there, regardless of your initial conditions. Within the equation, the dynamical equations that govern the evolution of these abundances that come from the Boltzmann equations coupled to the Einstein equation, you basically are, this is basically a global attractor solution within this system of equations. The universe is going to evolve toward this stasis fixed point, regardless of where you start. And here in this left plot, this is sort of a historical thing. So one can plot this in terms of the matter abundance and the Hubble parameter. One can also plot this in terms of the matter abundance and the average matter abundance since time t naught at any given time. I won't get into details. That serves as a proxy for Hubble. It's just easier to plot in terms of these variables. But basically, regardless of where you start, in this plane here, in the omega m average plane, you are going to evolve toward this red dot, which is the stasis solution. And again, this is for the example that I showed in the previous slide. So here, the stasis solution has omega m equals 0.5. And of course, the average, as we evolve into stasis, is eventually going to also become 0.5. Also, if you think, consider how things change if you have, for example, a different time scale for your decay of your heaviest mode, gamma sub n minus 1 here. Relative to the initial value of the Hubble parameter. Again, that's changing those parameters does indeed change the approach to stasis. Sometimes the system falls down, sometimes the matter abundance falls down. We have a lot of radiation, but then it's kind of so it undershoots, but then self-corrects, or sometimes it evolves down, as we've seen in the previous slide, to the stasis solution. But again, the stasis solution is an attractor. You're going to flow there, and as long as you don't run out of state before you get there, you're going to end up in stasis. So also, stasis, I've shown you examples here that involve matter and radiation, and I'm going to focus on these for the remainder of the talk, but I also want to emphasize that stasis is a very general phenomenon. Stasis can involve other cosmological components. For example, you can get a stasis involving matter and vacuum energy if you have a tower of oscillating scalar fields with a spectrum of masses. These transition from overdamped to underdamped behavior at a time scale where the Hubble parameter is roughly around the mass of the state. We showed this in this paper here. So basically, when you're sort of transitioning from slow roll to oscillation, those different phases have different equations of state effectively. And so therefore, when you have a set of these oscillating scalar fields that are rolling down their potentials and then oscillating, you can end up getting a stasis out of that. It is also possible to have a stasis that involves more than two components. That's something that I'm showing here in this plot on the right. This is involving matter, vacuum energy, and radiation. So basically, imagining a set of axion-like fields, which again roll down their potentials, oscillate, and then decay away to radiation. Again, so you have three different components there, effectively: vacuum energy, matter, and radiation, or slow roll, oscillating, and radiation, if you will. And those can give rise to a triple stasis. And there are even certain situations in which the pump can be facilitated by annihilation instead of decay. So you can have a single heavy particle species, which is non-relativistic, but yet in thermal equilibrium with itself, which annihilates into radiation with which it is not in thermal equilibrium. And that can give rise to a stasis as well. My point here is just to emphasize there are a lot of different realizations of stasis, and this is a fairly ubiquitous, robust phenomenon that appears all over the place in these kinds of theories that involve towers. And again, that's why this is interesting. It's not necessarily that we want stasis for any particular reason to solve any particular problem. It's that stasis appears in the landscapes of theories that we already know and love for other reasons. And that's why we really should care about it. Okay, so in the second half of my talk, I'm going to start switch gears a little bit here and talk about some of the observational consequences of stasis. So stasis can lead to a number of observable effects. It can modify CMB observable predictions given a theory of inflation for things like the spectral index or the tensor to scalar ratio. I'm going to skip this. If anybody really wants to ask me during the questions, feel free. I have some extra slides. But I'm going to focus here on the two what we think are sort of the most interesting possibilities here for how one might probe stasis. First of all, stasis can give rise to gravitational wave signatures in a number of different ways, and I'm going to focus here on the way that the modification of the cosmology can modify the stochastic gravitational background that's produced by other sources earlier on in the universe. Then I'm also going to talk a little bit about how density perturbations evolve during a stasis epoch, because this is different than the way they evolve in the standard cosmology, and that can have important observable consequences as well for the structure of matter at small scales. So these, I want to emphasize as I get going here before I get into the weeds, these effects, modification of the way density perturbations evolve and modification of the way, tensor perturbations as well as the scalar perturbations, gravitational waves, in other words, evolve. These are fairly generic things, right? If I'm modifying the background cosmology, these are the way perturbations evolve. That can change. So these are fairly generic consequences of cosmologies that involve a stasis epoch. However, for concreteness, I'm going to discuss these effects as we go on in this talk in the context of stasis models in which they are particularly interesting. And since I'm basically staring at my talk slides and I'm not seeing anybody, Anisha, how much time do I have here? Is it about 15 minutes?
Yes, we still have 15 minutes.
Okay, fantastic. All right, that'll be good. I'll go at a decent clip, but I'll be able to give you folks the idea. Okay, so first of all, gravitational waves. So the particular stasis model that I'm going to talk about here, the context I'm going to give, is stasis that involves primordial black holes. Primordial black holes here are going to be the tower of states. And so we'll consider a set of primordial black holes with an extended mass spectrum that looks like this. So the mass goes to some exponent alpha. Again, I'm sorry, this is I'm just using the conventions for things that are used in the literature. So this alpha is not the same alpha as the alpha before. This is an index that characterizes how the density of states scales this way. So it's a slightly different alpha, but it does still have to do with how the abundances scale. It's just not quite the same parameter. Okay, so how do I get a population of black holes like this? Well, fairly generically, if I have a set of density perturbations during some epoch after inflation, during which the universe has an equation of state parameter WC. A lot of people have pointed out over the history of particle physics that these gravitational collapse of these perturbations during such an epoch give rise to a set of primordial black holes with such a spectrum. And the value of alpha in this case is determined by the equation of state parameter WC during this epoch. Alpha is given by this combination of this function of WC. So we want this to be an epoch after inflation. So WC better be greater than -1/3, or the universe would still be inflating. If that's between -1/3 and 1, it turns out alpha is between -2 and 0. As we go forward, we're actually in the kind of cosmologies that we're going to look at, we're going to want WC actually to be greater than 0, so that the primordial black holes themselves have a chance to dominate the universe with their energy density, and that will actually put us between -2 and -1 for alpha. So you should be thinking about alpha going between -2 and -1, although it can go between -2 and 0, although we'll see there are some phenomenological issues with that. Um, Also, the range of masses for the spectrum of primordial black holes, the minimum and maximum masses are also constrained. So the minimum mass is constrained by basically bounds on the Hubble parameter when the pivot scale leaves the horizon. That gives you a minimum mass of around has to be greater than around 0.1 grams. If the heaviest primordial black holes are too heavy, they'll end up evaporating during BBN and screwing up things that we can measure. And therefore, this needs to be less than around 10 to the -9, 10 to the -8 grams. So this is roughly the span of masses we're looking at in our mass spectrum, and the range of alpha goes from -2 basically to -1, or -2 to 0. Okay, so evaporation is going to, of course, is a process which primordial black holes undergo, and this is going to facilitate our pump that's going to transfer energy density from matter to radiation, in this case, the matter being the black holes, the radiation being the Hawking radiation that they evaporate into. Of course, the story is that primordial black holes have a temperature. I was just at Pascoe in the UK and got a chance to visit Westminster Abbey and see that this is actually on Hawking's tombstone, which is kind of cool that that's there. But anyhow, basically this implies that primordial black holes will evaporate away, and the rate at which they evaporate is given here. The gray body factor for PBHs in the mass range we're interested in is approximately constant, so this basically goes like 1 over the mass squared. What this implies is that the time scale at which a PBH evaporates completely basically goes like its mass cubed, and this is as is just has been pointed out in a number of scenarios, which is relevant for PBH production, or sorry, for gravitational wave production from PBHs and other scenarios. This is very abrupt, right? So this is even more abrupt than particle decay in terms of how rapidly this happens at the very end of the lifetime scale, the life of the black hole. So basically, you can think of this as kind of being a lifetime for the black hole, in other words. Accounting for all of this correctly, the Boltzmann equation for the PBHs looks like this. So we have an expansion term, and here is the integrated contribution across the PBH mass spectrum of this is basically the rate at which we are evaporating energy density away into radiation. All right, so that's how PBHs can give rise to a stasis, and indeed you can check, and they do give rise to a stasis. So the stasis that they give rise to, and this is going to be important, W bar, so you can see on the left here, if we start with the universe entirely primordial black hole dominated, again, we come into a phase where there is a constant omega PBH, so constant omega matter for a very long period. How long that period lasts depends on what alpha is, and the equation of state parameter, given by the balance of matter and radiation here, also depends on what alpha is. So, okay. This is also an attractor, as we've seen in decay-based stases. So in this evaporation-based stasis, this is also a global attractor. Okay, so what does this mean for our cosmic timeline, our expansion history? Well, this basically means that from during the period of cosmology that we're interested in here, between the end of inflation and the BBN epoch, there are basically four cosmological epochs that we need to think about. First of all, there's the epoch during which the PBHs are generated, where you have this WC equation of state parameter for the background fluid, which is determining the value of alpha. Then you have an epoch during which the PBHs come to dominate the energy density of the universe. Of course, this doesn't have to happen. This depends on, what the overall abundance of PBHs is. But in cases, we're going to focus on cases in which this does happen, because that way you'll have a significant enough abundance for PBHs to get yourself into a stasis where the PBHs are providing an order one kind of contribution to the overall energy density. Then, once these PBHs begin evaporating at a reasonable rate, we basically end up with a stasis, as we've shown before, where in an epoch where the equation of state parameter for the universe is W bar. Now remember, this W bar was determined by the value of alpha, which was in turn determined by WC. These are one-to-one correspondences here. So you tell me the value of WC, I will tell you the value of W bar. These things are correlated. This is going to become important. And of course, since there are all sorts of other processes other than Hawking evaporation that PBHs are involved in. So PBHs merge, right? So a pair of PBHs decouples from the Hubble flow. They are attracted to each other under gravity. Some other disturbance in the gravitational potential by some local object, the nearest neighbor, some other perturbation or what have you, makes them vie away from having a head-on collision, and then they end up forming a binary, which ends up coalescing, and you get gravitational waves, and that's great. But you also get a heavier black hole. So this can represent a change in the primordial black hole mass spectrum. So this can distort your FPBH, your PBH mass spectrum. Accretion can also distort your PBH mass spectrum, right? And you might worry that these are a problem. It actually turns out that mergers are not. The total merger rate is always below, not horribly negligibly below, but significantly below the Hubble rate, so that you don't really care about this. And as far as accretion is concerned, there actually are meaningful bounds that you end up with on your parameter space. In particular, if alpha gets to be around -1 or larger, you end up with problems. Your PBHs accrete rather efficiently, and if you also have a very broad PBH mass spectrum, this can also cause problems. So accretion can put some meaningful bounds on your parameter space, but throughout most of the parameter space that's relevant for primordial black hole stasis, things are fine. And I'm happy to go into the details there if anybody wants to ask later on. But okay, so if you can get a stasis from primordial black holes, what will this do to the gravitational wave background? Well, for concreteness, let's consider a simple case of a stochastic gravitational wave background, which is homogeneous, isotropic, Gaussian, and unpolarized. So the differential gravitational wave energy density per logarithmic co-moving wave number k looks like this in this case. And this h sub k is the differential amplitude for the gravitational wave. This depends on when the perturbation re-enters the horizon in this way. So there's a 1/a scaling here. During an epoch wherein W is constant, and of course that's going to be true during each epoch, effectively, of our 4-epoch cosmology.
We have 5 minutes left.
Okay, great. I'll go pretty fast then. All right, so K basically scales like this. You plug this into the formula from the previous slide, and this basically implies that your gravitational wave spectrum looks like this and depends on K. It scales with K according to this power law here with this power law exponent. Note that this is a function of W. So the equation of state parameter tells you how things are going to scale with K, and therefore whether your spectrum is going to be flat or go down or go up during over any particular range of K. Now, if you think about the standard cosmology, plugging W equals 1/3 for radiation domination into this formula gives you 0. So that gives you a flat spectrum, and that's what you would expect in the standard cosmology. That's what I'm showing on the bottom. What do you get in this stasis cosmology? Well, we have many different epochs during which gravitational waves can enter the horizon. They evolve differently during those epochs when they enter the horizon, and so what you end up with is this broken power law behavior. So this is a giant big equation. Let's actually look at some graphs of what these look like. So here on the left, so if I take a look at the left-hand plot here, so I'm showing you a bunch of different gravitational wave spectra that can emerge from these different theories, and I've chosen the normalization here to be this of course can depending on the situation go up or down. There's quite a lot of wiggle room, but I'm showing you something here to be somewhat provocative and to show you that you could actually detect these kinds of signals at future gravitational wave detectors here, and I've put some of the sensitivities for proposed and existing detectors. Here's advanced LIGO right over here. Here's LISA, DESIGO, etc. Okay. So what do these curves look like? So these are the differently colored curves show different values of alpha, and the different regions with different slopes here correspond to modes that are entering during different epochs. So on the far right here, we have modes that are entering after the stasis epoch has ended, and we basically have segued on to the standard cosmology. In fact, for reference, the standard cosmology, this is this black dashed line where everything's flat, right? So if, however, I have a period of stasis, the modes that are entering the horizon are going to have they're going to give a different slope for the gravitational wave spectrum, and so depending on the value of alpha, this is going to go down. Then the second region is where we have the and I'll just put some guidelines here for the blue one so you can see. Second region is modes that are entering during PBH domination. Third is modes that are entering during the PBH production epoch. The point is that if you can build a detector that would give you sensitivity to the range up here at larger K, the modes that enter here, because the W's, the equations of state for the modes that enter here and the modes that enter here are correlated, then you actually kind of have a little bit of a smoking gun here that's basically saying if you see a correlation between this and this, that's kind of a hallmark of stasis. This is going to give you a particular slope. This is going to give you a particular slope. So and this region here, by the way, since of course we need an enhancement to the spectrum of density perturbations early on to get them to collapse into gravitational waves in the first place, there's also going to be these sort of cattail looking like little thick regions here correspond to regions where there's likely going to be an enhancement due to second order production of gravitational waves that come from these enhanced density perturbations. These are coupled through the Einstein equations, and these give you additional a contribution to the gravitational wave spectrum. So we expect an enhancement here too. Really rich phenomenology. Okay, since I only have 5 minutes left and have eaten into probably one of those 5 minutes, I'm going to go really quickly through the discussion of density perturbations, but this is another interesting possibility here. So I've mentioned that basically one of the cool things about stasis is that it can give rise to a cosmology where you have these epochs where the equation of state is constant, but it doesn't behave like a canonical value like matter or radiation or anything, and instead it mimics a perfect fluid that has some weird equation of state parameter that's constant that takes a value like a sixth or a ninth or something like that. So one might ask, this is a global thing, right? This is the equation of state globally for the universe. To what extent is this equivalence between a perfect fluid and stasis broken at the perturbation level? And to see that, you can consider what happens to the perturbations associated with some spectator component, call it chi, with the following properties. We're going to assume that this chi background component behaves like massive matter. It has a really, really small energy density or abundance throughout stasis, so it's not going to back react on Hubble or change or destroy the stasis or do anything to the background cosmology. And it interacts with other components only through gravity. In other words, it behaves like a population of decoupled, frozen out dark matter particles, and indeed that's the motivation. So think about what happens to a background dark matter component that's frozen out or that's already gained its abundance in some other way during stasis. So let's consider how the density contrast delta rho over rho for this chi component evolves during a matter radiation stasis, where W bar is between 0 and a third. We're going to see that the results differ significantly from what they look like in perfect fluid domination. Okay, so why? Let's see. So the spectator is decoupled, so it has no source or sink term, so its stress energy is conserved in this way. You can distill an equation of motion out of that for delta chi, and basically looks like a second order linear differential equation with a big old source term, where this phi is the Bardeen potential, which is up to a minus sign the gravitational potential. So you can think of this as a gravitational potential source. Since this is a linear differential equation with a source, I can solve it using the method of Green's functions. All I got to know is what the source is doing. Well, the Bardeen potential evolves according to the Einstein equation, and it turns out that it also is described by a second order linear differential equation with a source term. This source term, however, is the all-important thing that's going to give us the difference between stasis and perfect fluid domination. Let's take a look at what it looks like. So it looks like a bunch of prefactors, and then it's a sum weighted by the energy. So it's a sum over all of the different cosmological components that are in my cosmology, weighted by the background energy density for each individual component times its density contrast times the difference between the equation of state parameter for the universe as a whole. So this is either W bar or W for the perfect fluid, depending on whether we're talking about a stasis or a perfect fluid dominated cosmology, minus the effective sound speed squared for the individual fluid we're talking about. And then we sum all of those up. That's our source term. Okay, so in perfect fluid domination, what happens? So if I have a perfect fluid that's just a perfect fluid where it's, P equals W rho, that's its equation of state parameter where WPF is a constant. So if I have a perfect fluid dominated cosmology, there is only one component in this sum that has a non-negligible rho. And for this component, the W for the universe is basically W for the perfect fluid, and its sound speed is basically W for the perfect fluid square rooted. So C squared is WPF. So therefore, this difference here is 0, and this term on the right vanishes. This was noted by these folks here initially, and you can solve this equation using very simple methods. The solutions are basically Bessel functions times polynomials, and when you plug this back into the Green's function solution for delta chi, basically your spectator component, there's a little bit of a transient behavior, quote unquote, at the beginning, but then basically things plateau. So if you think about this in relation to the standard cosmology, where if you're in a radiation dominated background, matter perturbations grow like a log. This is actually a suppression because in the perfect fluid domination cosmology, matter perturbations do not grow at all, period. Okay, what happens in a stasis? Well, in a stasis,
We have 30 seconds left.
okay, I will go very quickly through this. In a stasis, the punchline is we have multiple cosmological components in our system. If we have matter and radiation, for matter, basically W equals the sound speed is basically 0. For radiation, this depends a little bit on plasma effects, but if you have pure radiation component or whatever, C is a third, even if it deviates a little from a third. The point is that you still have multiple components that have that don't have W bar equals C squared, and therefore the right side of this equation does not vanish. So the phi, the Bardeen potential, is actually falling monotonically and not ringing like a Bessel function. What does this do? It turns out that it gives rise to power law growth for the density perturbation. So after this initial transient, you can see a little bit of a slope change here. You segue into a region of constant slope where this power law exponent here is determined by what W bar is in the stasis, and it goes between, it's totally not obvious from this weirdly looking function, but it goes between 0 and 1. So in other words, depending on the balance of matter and radiation during your stasis, this interpolates, this power law behavior interpolates between what you get in radiation domination and in matter domination. If your W bar is very close to 0, meaning you have much more matter than radiation, the power law is very close to the linear growth, the Q equals 1 growth that you'd expect for a matter-dominated universe. If you study, for example, early matter-dominated epochs, this is what you get. And for radiation domination, it turns out that the transient takes over, and you do indeed get a log. But basically, in this regime, the W goes to W goes to 0 limit, Q goes to 0, and the transient takes over, and you segue into radiation domination. So basically, you interpolate between matter and radiation domination. Why does this matter? Well, this matters because the linear matter power spectrum basically goes like delta km squared. So this gives rise to an enhancement, but a characteristic enhancement that's different from what you get in an early matter-dominated era. And it turns out that the best case scenario, if you're having this happen right before BBN, is that you're enhancing things around sort of Earth-size or asteroid-size halos. These are microhalos, small dense clumps of matter that can have all sorts of phenomenologically interesting effects, like a cluster caustic microlensing, or basically at pulsar timing arrays. You can see Shapiro time delay effects from them. So there are all sorts of interesting observable effects to which this can lead, which we're exploring right now. So this, in summary, stable multi-component cosmological epochs of cosmological stasis, arise generically in a lot of well-motivated extensions of the standard model, namely those that include towers of states, and even some that don't, as I've talked about before. Such epochs have a number of implications for observational cosmology. They can alter the stochastic gravitational background in interesting ways. They can give rise to correlated and characteristic features. And density perturbations evolve differently during stasis than they do in either the standard cosmology or in EMDE, but still give rise to enhanced structure on small scales. So this could give rise to some interesting phenomenology in terms of the behavior of microhalos. All right. Hopefully I haven't gone over time too